Okay, now we go to the most important topic of today, which is real sequences. What is a real sequence? So the idea is that they are infinite lists of numbers. The lists in principle are completely free. In the next position you can put whatever number you want, whatever you prefer. So it is not a matter of ordering and so on. Okay? And this is the idea. And the rigorous definition if you really grasp the idea of function is clear what is the rigorous definition. The rigorous definition is nothing but a map whose domain are the natural numbers and whose target set are the reals. This is the rigorous definition, which means a function f from n to r that to every natural number n associates a real number f of n that is generally denoted by an. So you see there is the list of number, the following list of number is generated. You have a0, a1, a2, and so on, an. Okay? Whatever list you want. So in general there are two main ways to describe or to introduce a sequence. The first, by giving a law in the form of a function. So an is equal to some function f of n. Example, an equal to, I don't know, some polynomial n to the fifth power minus 7 n to the third plus 1, for instance. Or an equal to sine of n squared, for instance. Second, by recurrence. When I say by recurrence, I mean that the induction principle is used. So you do like that. First, you give a so-called initial datum, a0 in R. So this is the first step in the induction. Says what happens at n equal to 0. And then you know an, and you say that an plus 1 is equal to the image through the function f of an. So you give the first element and you give the generic element once its predecessor is known. So here there is the induction plane. We will mainly focus on this first type. I will say something about the second one, which is largely much more interesting. Much more interesting, richer, and also funnier. You have a lot to learn from this second sequences by recurrence. And if you want to learn a bit about them, you are suggested to read Chaos by James Gleick. Gleick is a journalist. He writes quite well about scientific stuff. And the second, which is much better, it's a French book, Hasard et Chaos, written by David Ruel, who is a Belgian, and he's one of the founders of the rigorous statistical mechanics. So he really had to deal a great lot about probability. Mm-hmm. So, to look some quite simple example about this recurrence, consider this guy. A naught is in R, a n plus 1 is, for instance, lambda times a n with lambda real number. So you start from a naught, then a1, which is lambda a naught, a2, which is lambda squared a naught, a3, which is lambda to the cube a naught, and so on, an lambda equal to lambda to the n a naught. This is an example of exponential growth. That is exactly what is worrying us now about the spreading of the second wave of COVID pandemic. It can be described, the process, by a simple mathematical object like that. A more interesting example from the point of view of the theory is the following. You have an initial datum a naught, which is taken somewhat randomly between 0 and 1, and then a n plus 1, which is 4 a n, 1 minus a n. So this is a parabola as a function of a n. So it is a very simple function. But the big surprise is that this sequence is highly chaotic, so highly unpredictable. I don't want to tell you nothing about chaos. I will give you an exercise where there is something chaotic to be handled, but without knowing that it is chaotic. But just to say that when you have to deal with sequences, something very advanced and very interesting can happen. Okay, you can find a lot of information about logistic map on the web. You go to the web and then you have fun. I suggest you to have fun with this structure. And this is called logistic map. Okay. So this is the idea of sequence and how sequence present. When you meet them, you can now recognize them. And now let me go to the problem of sequences. The problem, so what we will ask about sequences is to describe the asymptotic behavior, where asymptotic means for very, very, very large n. And symbolically we'll write always n much greater than 1. Okay? And so this is the idea. So in general, we will be not interested in A0 in 1 and not even A1 billion. But what happens, we will say, for n that goes to infinity. I will make this concept clearer and rigorously defined in the mathematical sense. But first, let me propose you some examples. First example is very easy. You have an equal to 1 for every n. It means the following. That here you have the real line, and here you have the number 1. And you can also imagine something like raindrops falling always on the same point. 1, and then again 1, and then again 1, and then again 1, and so on and so on. This is a way of thinking of the real sequences. You have the real line, and then there is a sort of rain on the real line. And when the rain falls, you can try to figure out some asymptotic behavior. Another way of figuring real sequences out is the following. If you know what is a graph of a function, and of course you know what is, you simply describe not a rain but a graph. But the graph has to be made by points 0, 1, 2. Okay? This is really the graph of a real sequence. Second example that will be very useful in order to construct examples and counterexamples. An is equal to minus 1 to the n. Again, n is a real number, and what you have here is the following. A0 is equal to minus 1 to the 0th power, which is 1. A1 is minus 1 to the 1, which is minus 1. So the first raindrop is here, the second here, and the third is again here, and the fourth is again here. So the sequence always jumps between these two values, minus 1 and plus 1. And the other representation is clearer, perhaps, because here we see that we start from plus 1, then we go to minus 1, plus 1, minus 1, plus 1, minus 1, plus 1, minus 1, and so on and so on. So this is the second example. The third example. Let me consider an is equal to 1 over n. And so in the first representation, what you have here is, okay, of course here n different from 0, so we start from n equal to 1. Here we have a1 equal to 1. Then a2 equal to 1/2, a3 equal to 1/3, then you have a4, a5, and so on and so on. And here is 0. Okay? And the other representation is clear enough too. Because here have one, 1/2, 1/3, 1/4. and so on and so on. And the last I want to propose you is the following. For an is equal to sine of n, and let me stress that n here are radians, not degrees. Okay, with degrees it will be much different and much simpler. With radians, it is quite complicated, because what happens here is that here you have 0, here you have -1, here 1. Of course, the whole sequence falls here between -1 and 1 because it is a sine. And you start from sine of 0, which is equal to 0. And this is A0. And then A1 is sine of 1, and sine of 1 is around here. And then A2 is here. A3 is very close to -1. Then A4 is back here, and so on and so on. But if you keep on going with these raindrops, you end up by believing that raindrops fall almost randomly here. It is not clear what is the asymptotic behavior. And the same for the other representation. The other representation can be constructed probably in a clearer way here. Okay. And so the clearer way means that you draw the graph of the sine, and then you start discussing it and just say that here 0, here there is 1, here there is 2, here there is 3, and so on and so on. So the points that you isolate on the curve are those. So A0, A1 is here, A2 is here, and so on and so on. A3 is here. Okay? This is how the sequence can be seen in the other representation. So, I gave you just this few examples. We will see many other examples, but my concern was to convince you that in general the asymptotic behavior can be extremely various. And I will add this word, which is somewhat strange in this context, but I would say unpredictable. But there are some particular cases the asymptotic behavior can be described quite easily. Here there are some in our example, some simple asymptotic behavior. For instance, for the first example, which is the constant sequence, all raindrops fall here. And here the level of the function is always the same. So this is constant. It is easy to say what happens asymptotically for n very, very large. Nothing happens. Okay, an also remains there. Then here we have an equal to minus 1 to the nth power, and we jump from here to here, and vice versa. And so, and again, the asymptotic behavior will change nothing. Here, we have a very interesting asymptotic behavior. You see that the sequence is going towards 0, always leftwards, and it never reaches 0. This is to be studied a bit. In the fourth, it is more difficult. We will understand then what happens. However, the first step will be to study behavior which is called convergence. So the next step and the next video is on convergent sequence.